So today I wanted to talk about, continue talking about homotopical co-completeness and completeness of model categories. And well, completeness, co-completeness, model categories. What's the meaning of this notion? Well, we have a certain idea based on what we know about regular completeness and co-completeness, meaning that model category is homotopically co-complete if there exist homotopical limit system. So just like in the situation of regular category theory, co-completeness amounts to saying that there exists a certain sort of diagram indexed by a category of small categories. So to rigorously define what does it mean, I first want to discuss left and right cut systems. Okay, so assume that we have a model category M, then a left or right cut system and M is a function f such that first for any small category D, f of D is the diagram category evaluated in M. Second, if we have a map on a functor in category of small categories, then it's of course not necessarily homotopical, although those categories are themselves not necessarily homotopical, so it doesn't really matter. We obtain a functor fu between diagram categories. And if we have a composable pair of functors, if we have a composable pair of functors, then we should have an actual weak equivalence called composer. So This is defined as a natural transformation, which in the case of a left system goes from the composition of functors between diagram categories to to the functor to the value of this system or this function in the composition. So this should be a natural equivalence. Or if we're considering a right system, then it goes in the opposite direction. Finally, well, not finally, but another thing that we require is that if we have three composable maps in the category of small categories, then we should have a commutative diagram or two commutative diagrams if we consider both left and right cut systems. Yeah, and if we consider the case of a right cut system, then the diagram goes in the opposite direction. And we call, so this is a cut system, and we call such a cut system is called homotopical. If for every functor between small categories, the functor Fu is homotopical. Moreover, we can define morphisms between cut systems. So so it is a function each such that for every morphism in a category of small categories, it assigns to it a natural transformation between Fu and Gu. And this natural transformation should commute with composers. Which means that for a left cut system, we have a commutative diagram like this. And so, of course, we can say when such a map is a weak equivalence. So H is a weak equivalence. If for any function between small categories, HU is a natural weak equivalence. H is natural weak equivalence. And so you see that we obtain a homotopical category of left or right cut systems, which we'll denote by cut L syst or cut R syst, depending on which type of cut systems we're considering. So this is a homotopical category, and we can consider a full subcategory spanned by homotopical cut systems. So as an example, which we already seen before, we can consider an arbitrary model category and then any colimit or limit system on M in the left, respectively right cut system. So now we can define what is a homotopic limit and limit systems, analogously to just colimit and limit systems for ordinary categories. Okay, so assume that M is a model category. Then homotopy limit system is a pair KA where K is a homotopical left cut system on M, or if we consider limit homotopy limit system on M, then it is a homotopical right cut system on M, and we should have a map E from K to cat system to the colimit cat system, which is a morphism of left cat systems. Or if we're considering a limit system, then we should have a morphism from limit system on M to K. Okay, and what are the conditions on this pair? First of all, for any functor U, the pair KU AU is a homotopy U colimit, or U limit if we're considering a limit system. I will refer from writing down this dual condition. I think it's pretty much obvious. And another thing is that Ka is a homotopically terminal object in the homotopical category of homotopical left cat systems on M over the system column cat. So can be abbreviated to this. So as you can see, this is pretty similar to what we required from just homotopic elements, say, because we required it to be a homotopically terminal object in the over category of functors over of homotopical functors over limit or colimit. Then we can see from homotopy uniqueness of homotopically eternal objects that if one object, this category if one object of this category satisfies 1 and 2, and if one object satisfies 1 and 2, then this weakly equivalent to any percentage object. So yeah, so they're homotopically unique. Now we can turn to the promised homotopical co-completeness and completeness of model categories. Okay, so let M be a model category. Then M is homotopically complete and co-complete. In a sense that there exists a homotopy limit and co-limit systems on M. And moreover, every object of this over category of left cut systems over the glim cut system satisfies either 1 or 2 from the previous point. Satisfies both. And this implies that it is such a colimit system. Okay, so let us prove this statement about homotopical completeness and cocompleteness. So let Rs be a pair of functions which assign to every small category T left deformation Rd as D, which deforms the category of diagrams into a full subcategory of virtually cofibrant objects. And for every left cut system, let TR denote function which assigns the following things. So if we have a functor U between small categories, then it should assign the functor KR U, which is equal to K U R A, and it is a functor from this category of diagrams to this category of diagrams. So basically, it's just this virtual cofibrant replacement followed by this functor induced on categories of diagrams. If we have a composable pair of functors between small categories, then TR VU the natural transformation sorry so yeah is a natural transformation which is a composition of the following two things. So we take TR V, compose it with TR view, and by definition it is the same thing as this composition of deformations and induced functors between random categories. So yeah, so we have a natural transformation from this thing to KV KU array. So basically this is a so it should be some kind of composer. So this natural transformation is defined in the following manner. So we use this SB, which is a natural transformation from R to AD to get rid of it from RP to AD. B. Sorry, not ADB, AD of M. And so we compose this natural transformation with a natural equivalence. So we have a natural equivalence which comes from the composer. And thus we obtain a transformation from KRV KRU to KRVU, which will denote by KRVU. Now we define another function. So that KS be a function which assigns to every functor U from A to B natural transformation KSU defined like this. So clearly K is a K is a left homotopical cat system. Then KR and KS sorry. Then KR is also one, so it is a left homotopical cat system. And we have a weak equivalence from KR to K, which is given by KS. So basically, what we did, we sort of constructed a cofibrant replacement of a homotopical cut system using a deformation into virtually cofibrant diagrams in the categories of diagrams. Okay. Moreover, since it's saturated and additionally we know yeah, okay, so since M is saturated and for every font from A to B, the font induced in diagrams is homotopical. It follows that FR is a homotopical left cut system. And the function fs is a map fr to f. So it is a map of left cut systems. Since KR and KS are natural in the argument K, we see that every KA in this over category of left homotopical cat systems on M over the colimit cat system. So every such object gives rise to a zigzag in this same category of the form A KR AS AR where AS as usual denotes the diagonal in this commutative square. So ER here is defined by the following formula. ARU is equal to AU array for every fundamental small principles. Now we see that the second point about existence of homotopical limit systems on an arbitrary model category is a consequence of the following state. Is a consequence of the fact that we can observe that so the existence of limit systems follows from the observation that for any functor between small categories, the initial transformation calling cut as RQ, which is by definition the same as calling cut as through RA, which is in turn equal to just calling Q as A RA in initial weak equivalence. The map volume cut as R from column cut R is also a weak equivalence. And so we've constructed a homotopical limit system by basically composing the standard colimit system, colim cat, with the cofibrant replacement functor R. It's, well, roughly speaking, this the same method we used to construct left or right approximations for Boolean functors. However, however, here instead of Boolean functor, we sort of have a functor from category of small categories, but it does not impede our ability to construct approximations by taking random replacement. So this proves existence, and the remainder of the proposition is also clear from homotopical uniqueness of homotopic terminal and initial options. Okay, so this concludes the proof of this statement about homotopic completeness and co-completeness of fundamental categories. Now we have to move on to reading model structures, and in the end we want to understand what are virtually fibrant and cofibrant objects in a category of diagrams. So yeah, let's talk about reading model structures. So first, let me briefly sketch what is going to happen. So the idea is that if M is a model category and B is some special kind of category, which is called radio category, for example, simplex category or something like this, then category of diagrams requires something known as reading model structure. Then we'll discuss a special case of a radio category with fibrant or cofibrant constants, which means that reading category with fibrant constants is a radio category such that for any model category M, the adjoint pair of functions, functors, that is column B and a functor constant diagram, are at the left adjoints of equivalent junction. Okay, so let's discuss the notion of a radio category. So first of all, what is a ready category? So this is small category B, and together with sort of increasing subcategory and decreasing subcategory. Such that first there exists a degree function from objects of this small category B to non-negative integers. So and this function is such that all morphisms in this subcategory of this increasing subcategory raise the degree if they are non-identical. And conversely, maps in decreasing subcategory lowered. Once again, if they're non-identical. Moreover, every map B admits a factorial factorization as an increasing as a decreasing map followed by an increasing map. And so, if we're given a ready category, then we can define a ready model structure. So let's formulate the proposition which will define necessary classes of maps in the diagram category. So assume that we have a model category and B is a ready category. Then the category of diagrams from increasing category it means model structure such that weak equivalences and vibrations are objectivized ones. Oh, basically this can be said for any category of diagrams in the model category, where the indexing category is a small category. So this, I think, is called the projective model structure. And then, but here we wanted to precisely for this increase in subcategory. Yeah, okay. Thank you for this comment. Yeah, probably B minus and B plus. Okay. So obviously we can state the same thing about a decrease in subcategory, and there we require a model structure such that weak equivalences and cofibrations are objectivized ones. Objectivized ones, yeah. So now we can define a model structure on the whole category itself, which is sort of intermediate between injective and projective model structures, namely that we don't require fibrations or cofibrations to be objectivized ones, but instead require them to be sort of induced from these subcategories of diagrams from an increasing and decreasing subcategory. So MB admits model structure which map is a weak equivalence of vibration or vibration if its restrictions to both increasing and decreasing subcategories are so the sense of 1 and 2. So this description is not very explicit, and I think more often reading model structure is constructed in terms of latching and matching objects, and we will do it in just a moment. But first I want to formulate a certain corollary of this proposition. So if we have a functor, if we have a Boolean adjunction between two model categories, And then for every media category B, the induced junction is also a covalent junction. For the redeemable structure. Okay, so now let's discuss a more explicit way to define various classes of maps in media model structure. And first we introduce the concept of matching objects. So assume that we have a model category. Assume that B is a reading category. And assume that X is a diagram of sheet B in M. And for every object D in category B, one can consider the maximal subcategories so we take this over category of B over B, and we take it as a subcategory. So this thing here is a maximal subcategory. Which does not contain the map 1B. And similarly, we can define maximal subcategory of the undercategory of decreasing category. And we can define the latching object L P by taking it to be the colimit over this subcategory of the functor, of this diagram where J is a forgetful functor from this subcategory into the category. And similarly, we define matching object as a limit like this. Now we can explicitly describe Ready model structure. So let them be a model category. Let me be a Ready category. And assume that F is a map, natural transformation between diagrams. We say that F is a quick equivalence if it is an object-wise equivalence. We say that F is a trivial cofibration or just cofibration if for every object B in this B curly, the induced map taken from this co-product of, also I didn't say that F is from, that's the web, so yeah, so if we have this co-product, then we have an induced map to YB, and this thing here should be cofibration or trivial cofibration. Similarly, F is a fibration or trivial fibration if for any B and B curly, the induced map from XB to YB with MXB over MYB is a fibration or trivial fibration. Now we can define so now we can define a special class of Ready categories, namely the announced categories with fibrant or cofibrant constants. So let me read the category. And then we say that B is a category with fibrant cofibrant constants. If for every other category the junction between MB and M is equivalent. So this is the case of rigid category with fibrant constants, and if we write down the same thing in reverse for limits, then we will obtain category with cofibrant constants. And we can formulate a necessary and sufficient condition for this to be the case, because this requirement that for an arbitrary model category something holds seems rather abstract. So actually, this can be reformulated in purely internal terms for this rigid category. So let B be a rigid category. And then is a category with fibrant constants if the decreasing subcategory is a disjoint union of categories with a terminal object. And so for cofibrant constants require that the increasing subcategory is disjoint union of categories with an initial object. Okay, so let us sketch the proof. So the basic idea is that, well, so the requirement. So if this decreasing subcategory indeed splits into disjoint union of subcategories with a terminal object, then it is pretty clear that we indeed have Wheeler junction. And to show that the converse is the case, we can consider M equal to the category of small sets where cofibrations are monomorphisms. Fibrations are epimorphisms. And weak equivalences are isomorphisms of sets. And then the requirement that the diagram system of a one element set Suridi vibrant, and hence it implies that this category splits into desired subcategories. Okay, so now we can derive a corollary from this proposition. So if M is the model category.
Can I ask a question?
Yeah, of course.
Yeah, so I was wondering how, so is an Eilenberg-Zilberg category also, is it also a 3D model category?
Sorry, I probably don't know what is an.
So I think if you're talking about the Eilenberg-Zilberg, I mean, I'm not sure, but I think, yeah. So I know that they are, so you have a notion of a generalized 3D model category. So I know that, but I'm not sure. So it is, yeah, so it is, so yeah, so it is like a generalized 3D model category where you have similar subcategories. I mean, yeah, where you have, so if you call it, so yeah, if you call the category to be, say, R, then so you have the R plus will be monomorphisms and R minus will be split epimorphisms. Otherwise, it's almost the same.
Mm-hmm.
So, anyways, so yeah, we can talk more about that later.
Okay. Okay.
Yeah, sorry to interrupt you. Continue.
No, it's okay. Thank you for the comment. Yeah. So, okay, so FEM is the model category. And B is a video category. It's vibrant constants. Such that it has an initial terminal object B0 and X a diagram of shape B. It's a critical vibrant. Or vibrant. So it's really a vibrant diagram. Such that all maps there are weak equivalences. Then such that X so B is a weak equivalence for any morphism B and P. Then induced map X B0 to this B co-element of X is also a weak equivalence. Okay, so now so now let's move on to well, a very common example of ready category, namely categories of simplices. So assume that we have a non-negative integer, and N is a sort of chain category that looks like this. So we have a unique morphism I to J if and only if I is less or equal than J. Assume that D is a small category. Then category of simplices of D is a category with objects being functors from various M from, well, various categories of the form n to d for all n greater or equal to 0. And maps in these categories are of the following forms. So assume that we have a functor e1 and we have a functor e2. Then we call map we define a map between two such functors as a commutative triangle of the form like this, where the map from n1 to n2 is just some functor, or as can be easily seen, it is a non-decreasing map of it is a non-decreasing map of sets, if you want. But that's the same thing as requiring that it is just some functor between these categories. And so we'll denote by delta d this category, and delta d op will be denoted by delta op d. So delta d and delta op d are real categories. With vibrant and covibrant constants. Oh, sorry. With so this is a category with vibrant constants. This is a category with covibrant constants. With covibrant constants. Okay, and how we define this subcategories? So in order to define an increasing subcategory or equivalently a decreasing subcategory in the opposite category, we say that the increasing subcategory consists of such maps in this category where this functor between this chain categories is 1-to-1. Map the triangle, and decreasing subcategory or increasing subcategory in the opposite category consists of such maps where the upper map is onto this triangle. Now it follows from the description of categories with fibrant and cofibrant constants that we have equivalent junction. And this functor of limit sends radioic equivalences between radio cofibrant diagrams to weak equivalences between cofibrant objects. Moreover, one sees that given a functor between small categories U, we obtain equivalent junction So this looks like this, or we can write the same thing for the colimit and the induced diagram functor. So this result about send Ricci weak equivalences between Ricci cofibrant diagrams to weak equivalences between cofibrant objects can be generalized using something known as projection functors. So assume that D is a small category. And we define a terminal projection functor T and initial projection functor Pi as functors from the category of simplices in T to D and opposite category of simplices such that here E from N to D is sent to En, and here E from N to D is sent to E0. Now, it is not that hard to prove that, first of all, for every object D in D, and the overcategory of this object coincides the category of simplices in the overcategory of this object in the initial category. And we have a dual statement for the initial projection factor. And the second statement is that, well, this is a direct generalization, that if we have an arbitrary function between small categories, and B is an object in P, then the overcategory of B is the same as category of simplices of this overcategory. Now these observations, together with the results we've already proven, and with just the definition of the category of simplices, imply the following proposition. So assume that M is a category, and then for every small category D, the functor, the colimit functor of the terminal projection from the diagram over from diagrams over category of simplices to diagrams over category itself, or if we have a functor, then we can consider such colimit. So these functors send Breeder with equivalences between Breeder cofibrant objects to object-wise with equivalences between object-wise cofibrant objects. Objects with diagrams. I think it's better to say diagrams here, so it's not to confuse all this object-based stuff with objects of diagonal categories. Okay. So, well, I don't think that I will be able to cover the next part I wanted to discuss, namely virtually covibrant and vibrant diagrams. So I think for today we'll have to stop here.
Thank you.
Okay, sure. Thank you so much for attending, and we can certainly discuss. So let me stop the recording first of all.